Welcome back to a new video. In this video we will discuss a capacitor multiplier circuit. This circuit is very useful in order to create larger capacitor values from a relatively small capacitor. This will be very handy where you have a very low frequency cutoff in your low pass filter design. Of course we will see shortly everything step by step in our calculations and verify these in SPI simulations. Now before we jump to the calculations and the design example, let's first do the derivation of this circuit. This multiplier or capacitor multiplier is shown here. You see here two operational amplifiers, two resistors and one capacitor. Now what we want is the capacitance between these two nodes, which is some multiple of this capacitor what we have here. So we need to have an input impedance relationship between these two nodes. Before we dive into the calculation, let's designate first the nodes A and B here, and also the currents here for this resistor I1, I2, and also the capacitor current IC. Now, in order to also continue with the next analysis, we also designate here the node T. Now, the goal is expression for the impedance Z in, so input impedance. Now, from there, we can then relate that to the capacitance using the formula for the reactance of the capacitor. Okay, we know that the input impedance Z in is equal to the voltage at this node, Vt, divided by the current, and that current is the current here through the capacitor. Why only that capacitor current? Because the current in the op-amp is in ideal case 0. So this is the expression we will use in order to continue and calculate the Z in. Now, due to negative feedback for op-amp or operational amplifier X1, we have that the VA, which is this node voltage, is equal to Vt. Now, from node A to node B, that is actually from this node to that node, we have in fact an inverting amplifier circuit. And we know what the gain is of this inverting amplifier circuit in the voltage gain. And that is then given by this expression. You see here the VB is equal to minus R2 over R1 times VA. Okay, now we have now these two equations. Now we can say the following. We can also write that the VB is equal to minus R2 over R1 times VT, because VA is also equal to VT. Now let's designate this equation number 1. Now we can also look at the capacitor current IC here, and that is this current is equal to the voltage at this node minus the voltage at that node, so voltage at Vt, minus Vb over the reactance of this capacitor. Now, in the Laplace domain, that can be then written like so. So because the reactance of capacitor is 1 over the SC, and this is the voltage at node T minus the voltage at node B, and you see here the reactance in the Laplace domain. And now that can be also written like so, because you divide by a ratio, so you can actually write it like so. And then we see that we can also use this equation and this equation together to get to this Z in. Now, let's now also substitute equation number 1 in this equation number 2. Then we have the following. You see now here the IC, which is the capacitor current, will be Vt minus this ratio R2 over R1 times Vt, and that is now of course plus, and you see now here everything in the parentheses times Cs. Okay, now we have our expression of the capacitor current. Let's now continue in order to go to this Z in. Now we can now bring this Vt out, because we see here 1 plus R2 over R1 and then in the parentheses times Vt. You see now here an expression. We can now also divide the left and right hand side such that you have an expression which is then Vt over Ic. You can also see it like so. This cross multiplication will result in this expression also. So we see now here already what we wanted to have, because this expression has this Vt and Ic, and I have here 1 over this 1 plus R2 over R1 times Sc. Now we can a little bit write it in different ways, such that you have an S, again this Laplace parameter in front, and then times 1 plus R2 over R1 times this capacitor C. We see here or recognize actually that the input impedance now is given by this expression, because this expression was Z in. And in here we see that this part, which is actually 1 over S, a new expression of the capacitance, which is then our equivalent capacitance CT. So our Z in also written like 1 over SCT. And that is then given by this expression. You see now here clearly that the capacitor C which you have here is multiplied by some constant, which is 1 plus R2 over R1. It can be, of course, 10 times, 20 times, depending on the ratio of these resistors. So we have a nice expression that can now make this capacitor looking larger between these two nodes. Okay, so again, the capacitor is multiplied by this factor, which is the 1 plus R2 over R1. Let's now go to an example. The first example about the creation of a capacitance of 2 millifarads from 20 microfarads. And again, our circuit, and again, this needs to be a capacitor CT, which should be then 2 millifarads. From, of course, this capacitor, which is then 20 microfarads. Again, our formula. Now we can do the calculation here. We see that the CT must be 2 millifarads, and our C, what we need to use is 20 microfarads. And this is the formula we need to use. And it can be then written like so. So CT over C is equal to 1 plus R2 over R1. In this case, this design is really based on the calculation of the values of R2 and R1. So R2 over R1 will be then CT over C minus 1. Now we know everything here, so we can now have the relationship. So 0.002 over this 20 times 10 to the power minus 6, that's 20 microfarad minus 1. And that is then 100 minus 1 will be 99. So the ratio of these two resistors must be 99. Now we can now select the resistor R1, for example, 1 kilo ohm, then the R2 must be 99 kilo ohm in order to have this ratio 99. Let's see the simulation result. This is now the body plot. You see here the curve. The horizontal axis given in the log scale, but also the vertical axis given in the log scale. So this is the impedance of that circuit here. This is, by the way, the circuit in the Tina TI Spice. You see the resistor R2, R1, the capacitor of 20 microfarad, and the two operation amplifiers. We measure here using this ohm meter or impedance meter between these two nodes, the ground and this node here. And this curve here shows some labels, and let's go here, for example, at this label at 10 Hertz. You see a impedance of 7.95775 ohm. So what does it mean? Now again here, the impedance is 7.95775 ohm at 10 Hertz. And we know that the reactance of the capacitor looking between these two nodes must be also this at 10 Hertz. And the formula can be then written in this format. You see here again the reactance of this total capacitance is equal to 1 over omega times the CT. Now we can rewrite this such that you have an expression for CT, and that is then given by this expression. You see again the omega and the reactance of that capacitor. Now we know that we also can write the omega as 2 pi f, and that is also shown here. Now we can substitute here the values for the frequency of 10 Hertz, 2 pi times 10 Hertz times this impedance here. And now our capacitance, total capacitance between these two nodes is then 2 millifarads as required from this design. So this is indeed as expected. Okay, let's go to the next example. A little bit more practical situation where you have a sensor. It's modeled by a voltage source, which is in series with the source resistor given by this 8 ohm. So our model is shown here. You have now here this voltage source and the resistor RS. So our design is, we like to design a low pass filter with a cutoff frequency of 70 Hertz. So how do we do that? What is now the solution for this situation? Now our sensor with our low pass filter can be then also given by this circuit. You see here again the voltage source and the source, which is our source resistor. So these two, again, the sensor model, and we have here the capacitor, and we create here the low pass filter. And we know the cutoff frequency of this circuit, that is given by the 1 over the 2 pi RSC. Okay, now we know that the RS is given. We know what the kind of a cutoff frequency we need, so we can calculate now the required capacitor here. And that is then 1 over the 2 pi RS times the cutoff frequency. Now, if we now substitute here everything, 1 over 2 pi times 8 times 17, that will result in 1.17 millifarads, which is quite large in most cases, which is not maybe practical also for most PCB designs. So how do we do that? Indeed, we can now use our capacitor multiplier circuit. So we can use this circuit. You see here again the sensor and its source resistor. And here we see the circuit we have discussed earlier, and that is the complete equivalent circuit of the capacitor CT. And that CT was related to that capacitor C, which should be then pretty small, by this ratio. So we have here now that we can select the capacitor, in this case more convenient value of 20 microfarads, and then we need to create now a CT which is then 1.17 millifarad according to this design. Again, you bring up this equation. Now we can say again R2 over R1 must be then CT over C minus 1, and that is then equal to 1.17 times 10 to the power minus 3 over this 20 microfarads minus 1, and that equals 57.5. So we can now select the R1, for example, again 1 kilo ohm, and then we have R2 is then this much times R1, and that is then here as 57.5 kilo ohms. So we have the two resistors we require for our capacitor, which is then 1.17 millifarads. Okay, let's bring everything here, and then here the calculated capacitor, and I mean the selected capacitor value and the two resistors we just calculated. And now we have the simulation result. You see here the Bode plot. You see here again the circuit in the Tina Ti Spice, the RS of 8 ohm. We see here the two operation amplifiers and two resistors, and the capacitor of 20 microfarad. And here is our output. So we measure actually this node, and in this case we see here the complete circuit, which is then the equivalent of this CT, which should be then 1.70 millifarads. What do we see? Let's see that. So we have now here an minus 3.01 dB, which is the definition of a cutoff frequency, looking at the baseline of 0 dB at 17 Hertz, which is indeed as expected, so as required also for this design. Alright, it was our example considering the capacitor multiplier circuit. We have first looked at the capacitor multiplier circuit on its own, and then use that in the low pass filter design for a specific model of a sensor in order to create a very low cutoff frequency. If you have any questions, comments, please let me know, and I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation, and see you next time in another video. Take care.